This is the lecture over Chapter 6 of your textbook. It covers arrays. In this chapter, we'll talk about what an array is, how you can use arrays to make decisions or to replace nested decisions, talking about using constants, which I don't think we've done a lot of, and how you might do that with arrays, searching an array for contents, using a concept referred to as parallel arrays, searching an array when we want to match for a range. For example, if a value is 1, 2, or 3, we want to do this. If it's 4, 5, 6, we want to do something else. And then we'll talk about a for loop, which are very often used in processing arrays, in particular when you want to process every element of an array. So, what is an array? It's basically a series or collections of locations in computer memory that are grouped together into a data structure that we refer to as an array. All those locations share a common name. They must be of the same data type. That is, if we store numbers in one element of array, then all the elements of the array are going to be storing numbers. And then the way we pick elements out of an array, specific memory locations, is using something called a subscript or index. Most of the time I will probably use the term index. So an array is a chunk of memory that has the qualities that we talked about before. An element refers to a single element of the array. The size of the array is how many elements it can hold. So if we say we have a names array and it contains names and there's 10 of them, then we can hold up to 10 names. The subscripts or indexes or indices is how we pick an element out of the array, and these are always going to be integers. And one thing they don't mention here is they're always going to start at 0. Putting values into an array, they say it's populating an array. You might also say storing elements in an array would be another way to word that. So here's an example. If we think of this two-dimensional table as memory, somewhere in memory it looks like we have a 3-element array. It's referred to as prices. If we say prices, it refers to all 3 elements. But if we put an index or pick a specific one, then it refers to one of the items in the array. One thing to notice here is that indexes start at 0. So n runs to 1 minus or 1 less than the size of the array. So some things we could say about this is we have an array called prices. There are 3 elements. Those elements are indexed by 0 through 2. Again, noting that 2 is 1 less than 3, the number of elements. In this case, we have numeric values. All the locations in this array would therefore have to be numeric values. So throughout this chapter they give several examples. So here we have a list of employees we have a list of employees, and then we need to know how many dependents they're claiming so that we can, figure out how much taxes to withhold. So throughout this chapter, and I may change this slightly or give an example, they assume that no employee is going to have more than 5 dependents. Now, in real life, that probably covers 95%, but there are families that are much bigger or have more than 5 dependents in them. So what we're going to do is we're going to start out using what we know to this point and just make a set of decisions and have multiple count variables so that we can generate something similar to what's shown in Figure 6.2. They make the statement that the application does not need to scale for more than 5 dependents. In the real life situation, maybe once you get more than 5 dependents, it doesn't really matter if you have 5, 10, 15, your taxes are going to be the same. Or maybe they're just making an assumption to make the programming a little easier. So in real life, we might have to think about that a little bit. So using what we know to this point, one way to do this would be we're going to prompt the user for a number of dependents. Notice at the top they have what they call significant declarations. These are basically count 0 is how many people have 0 dependents, count 1 is how many people have 1 dependent, or etc. Last chapter we talked about how running totals start at 0 and running products start at 1. So we're going to have a running total of the number of dependents. So all these counts, 0 through 5, need to be initialized to 0 for the program to work correctly. So then what we do is we get a number of dependents, DEP, from the user or from a file, which we'll talk about in the next chapter. And then what you do is you just have a whole bunch of decisions. If dependents equals 0, increment count 0. If that's not true, if the dependents equal 1, then increment count 1 by 1, etc. So we go through and we have 5 decisions, and once we find the right value, we increment the associated count, and then we fall out of this decision. So this is one way you might go through and solve the problem. With arrays, though, it's probably not the best decision. So what we can do is they make a claim that array reduces the number of statements needed. And we'll see that the code or the flow chart is much shorter here in a moment. So what we're going to do is, instead of having 6 variables, count 0 through count 5, we're going to declare a single array. That array will have 6 locations, one that matches up for count 0, count 1, etc. And then what we're going to do is we're going to use a variable to act as a subscript into the array. And then what we will do is we will say that associated location, add 1 to the value stored there. So we'll be storing our accumulators or our running sums in the array. So just to repeat again, subscripts have to be integers, which means they have no decimal value. And then what we're going to do is often as you go through, you start at 0 and then you increment by 1 each time to pass through the loop. So when we go to, they'll definitely be true when we go to print out the results. So what they've done here is, instead of having 6 independent variables, they've declared an array that has 6 locations, and up in the declarations at the top left, you will see that they initialized each of those locations to 0. Now the flowchart and the pseudocode looks very, very similar. The only difference is, instead of saying count 0 equal count 0 plus 1, for example, at the top, it says counts array index 0 equals what is currently in index 0 plus 1. So that didn't really buy us a whole lot. You know, we even had to type a few extra characters. So as far as typing this out, or the size of the file, it actually got a little bigger. And that's because we haven't done something to greatly simplify that. Notice at the first decision, if we take the yes branch, dependent equals 0, we'll notice that the index of our array is 0. If we go down one more decision where it says dependents equal 1, notice that the index is 1. So we can probably use that fact to make this much simpler. So that's what they're saying here is, you know, we haven't improved our process. So how can we go through and make this better? Well, what we can do is, as I pointed out, when dependence is 0, we were using index or location 0 of our array. Location is another way to refer to an element. So if our dependent is 0, then count 0 will equal count 0 plus 1, substituting in for the value of DEP. And in the last case, you know, if we fall through and dependence is 5, it will increment the 5th location of the 6th element array, so the last element of the array. So you kind of need to think about, you know, how all those values relate to each other. So what they've done here is the flowchart looks a little bigger, but that's because they did this in their good programming style. So in the case of get ready, we need to prime the loop that we're going to have and ask for the number of dependents. And if we type quit, we're supposed to terminate the program. Otherwise, we're going to assume that the user inputted a valid value of dependents. And then what we do is we go in, we increment the correct location in the array, and then we prompt for the next number of dependents, again telling the user to type quit to quit the program. So we have a loop that goes through, and based on that value, increments the correct location in the array. Now, once we get to the bottom, we need to output our results, which we haven't talked about yet. So they're going to go back and set the dependent variable to 0. They're going to output location 0 or index 0 of the array. They're then going to increment that to 1, and then they go back and 1 is less than 6. So we output the second element of the array, index 1. And we do that till we get to 5. And then once we print out the location 5, that's the last element of the array. DEP will be incremented to 6. The statement or the question 6 less than 6 is false. So we will drop out of that and our program will ultimately terminate. So by finding ways to tie information to indices or locations in the array can greatly simplify the code and our thought process. So this they've just gone through and shown the pseudocode for what I discussed previously in the flowchart. So we won't spend a lot of time on that, but you should hopefully be starting to feel comfortable with either writing a flowchart, writing pseudocode, or taking one and converting to the other. Like I said, hopefully you're getting comfortable with that. So, constants. We talked about this in a previous chapter. I don't recall which chapter, but basically it is thought of as a variable whose value can only be set once and never changes. So there are several ways that we can do this. A very common one is to hold the size of an array. When we define an array in BASIC, this is not necessarily true for other languages, but in BASIC is one of the languages that this is true for. When you set the size of the array, that is the size of the array. It can't get any bigger, it can't get any smaller. Now, you may not store information in every location in the array, but memory space is allocated. The indexes exist to be 0 to that size minus 1. We can use them as array values. That's probably not super common, and or to indexes or subscripts into the array. They say to avoid magic numbers. That's what they're calling unnamed constants. So if we just use a constant value and just hard code 10 everywhere because we have a 10 element array, they're really saying you should give it a name like size or array size or something like that is a little more descriptive. So if somebody's reading the program or you're coming back at a later point in time, you have some idea what you were thinking and what that value might be. You need to make sure if we're using this constant as the size of an array, then the indexes have to be less than that constant value. So if we say the size of the array is 20, our subscripts are going to be 0 through 19. So you need to make sure that we don't try to stick something in location 20. We don't try to stick something in location 21 because those do not exist in the array. Now, we'll talk in a moment what some possibilities are if you try to do that. Hopefully you get an error, but that's not always the case. Constants are created automatically in many languages. That is, if you use the value 10, there are some languages that are going to give it a generic name like constant 1 and define it to be 10. Here's something that I use quite often. We'll talk about what they do in the book, and then I'll talk about what I do, which might be slightly better. But they're going to be looking up the names of the months. So we declare an array called month. That's a descriptive name. It's going to have 12 elements because there are 12 months in a year. And then what they do is they define January, February, March, etc., all the way through December. So that's the array. Now, January is in location 0, and December is in location 11. So what we would have to do is, take a numeric month, let's say, subtract 1 from it, and then look up the element in the array to get the correct month. What I like to do, what I would personally do, is I would declare a month to be a 13 element array, and before January I would just put double quote, comma. So location 0 is the empty string, but location 1 is January all the way up to December being location 12 in that case. And then you could just take the numeric number and pull out that element of the array and not have to do math, or worse yet, try to do some math and get it incorrect, and then have the program, you type in 5 and it says that's June or that's April. Obviously we want it to say or use the value May. Here's an example of using a constant as an array index or an array subscript. So what they're doing in this case is they're trying to, let's say, keep track of sales numbers by state. And Indiana is the 5th location of the array. So anytime we wanted something about Indiana, we could just put Indiana and it would pull out the correct location of the array. Now, if I was doing this, would have to think about this. If we listed all the states in alphabetical order, I'm pretty sure Indiana would not be 5th in that list. So if it was me, I would actually go through, list all the states in alphabetical order, and then take the first one and say its value is 1. The next one, the value is 2, etc. But you wouldn't have to do that. You might have reasons for, assigning different values, but not knowing more about the problem they're trying to solve. That's just one comment I have. Now then, talking about searching an array, which is going through and looking for a particular item. Before, in the previous example, where we said location Indiana, that's a direct access to the array. We go into the array, we go straight to the index 5, which is the 6th element in the array, and we pull out a value. So that's how you directly get to a value. If we're looking for a particular value, we might, or checking for a certain set of conditions, we might do something called a linear search, which is basically we start at index 0, go 1, 2, 3, all the way up to the maximum index, looking for or performing whatever action we need to on the array. So here's some examples. In the first one, you have item numbers that are 3 digits, and they're not consecutive. So you have an array of these item numbers. There's no way to match them up with an index. They're just in some, let's assume, random order. So an employee or a customer comes in and says, I need part 330. So the first thing you need to do is make sure the item number is valid. So what happens is we would go through the array starting at location 0 and saying, does this location have 330? No. Go to the next one. Does it have 330? No. Let's go to the next one. And we would search through the array. If we did find an element that contained the part number 330, then we would fall out of the array and know that we had a valid item number. Now, if we make it all the way to the last element of the array and say, is the last element of the array 330, and the answer is no, then the item that we are searching for is not a valid item number. And then we would, somehow indicate that, possibly through an error message or something else. So here's an example flow chart where they've gone through and put some numbers. I said we would assume that they were in no particular order. It looks like they put them in numerically. But, the logic I talked you through before this slide still is valid. So what they're going to do is they're going to have a variable called foundit. And foundit is going to be, we assume false if you didn't find it. It's going to be yes if you did. So you go through and find the element and then set the value of find it. So this is continued on the next slide. So here's the interesting module called find item. So you set found it to no or false. You set your subscript to 0, and then you check, am I still in the range of valid subscripts? That is sub less than size. If yes, then I check that location. Notice that they use sub as the index into the array valid items. If that equals the item number we're searching for, we set found it to yes. Otherwise, we set it to yes, and then we go ahead and increment the sub variable. I'll talk about that in a moment if they don't take care of this. Then we go back. Are we still less than size? Yes, we do it again. So there's a couple of problems with this as far as efficiency. If this is a 1,000 item array and we find it in the first element, this is still going to search the other 999. So if I was writing this program, that very top decision, I would say if not found it and sub is less than 0, repeat the loop. That's kind of similar to short circuiting we talked about in logical expressions. Then you would fall out either by finding the element or going all the way through the array and not finding it. And then you would say, if you found it, you would say, yes, that's a valid part. If not, you would say, no, we didn't find it. And then also, for some reason, they want to know how many times we search for a bad item. So they would increment the bad item count by 1. Once you typed finish to quit, then we would exit out of the loop and, possibly give a summary or go ahead and do whatever we needed to do next. So here is pseudocode for the same process, kind of highlighting the important things that we talked about before. So we don't really need to talk about that again. That variable in the previous example called foundit, we refer to that as a flag. A flag typically has a true or false value, and basically in this case it's a flag to indicate did we find the variable or not. Setting it to no or 0 or false would be ways to indicate that we didn't find it. Setting it to yes or 1 or true would be a way to indicate that we did find it. So basically what they're doing here is they're summarizing what we just talked over, but in a more generic way. If we're going to use a flag, we set the flag to 0 or false. We then set our variable that's going to index through the array to 0, and then we examine each element of the array. If we find a value that matches, we're going to set our flag to true, and if it doesn't match, then we're just going to continue on looking for the next item. So the concept of parallel arrays. In some languages, you have to use this to accomplish what we're going to discuss. Other languages, you might just do it because it's fairly straightforward or the way you know to do it. But using parallel arrays is the concept of having two or more arrays, and let's say we have 5 arrays, and we're looking at location 4. Location 4 in all 5 of those arrays would contain a piece of data that was related to the same item, the same person, etc. In the example here, they say let's keep 2 arrays. Let's let them each have 6 elements. The first element is going to have valid item numbers, and then matched up with that, the second array is going to have item prices. The very important thing here is location 0, part number, its price needs to be in location 0 of the price array. So they have to match up in the same position. So what we would do in this case, going down to the bottom, is we would look through the array for the customer's item. Once we found the position of that item, we would then look at the corresponding position in the price array to know what the price was for that item or how much to charge the user. So here is an example of them in memory. They might not line up nice and pretty like this. They might be end to end or something. But to show you and to stress that the various locations have to contain related information, they kind of lined them up. So we have 2 6-element arrays. Part 457 is in location 4. So if we needed the price for that, we would go to location 4 and valid prices and find out that that item is $17.50. The first thing about parallel arrays we've already discussed. There's no direct relationship. We can't do something like, the part number, the price is 2 times the part number or something like that. That very rarely are we going to find a direct relationship for something like that. So we, use parallel arrays to do the association, in this case item number to price. Here's the flow chart. We're adding pricing information, so we have a price variable now that we can store the price in, and then we added the array valid prices. It's going to be the same size. Wouldn't make sense for it to be a different size, so we have a size constant that's set to 6 that we use throughout this. First of all, for doing the array declarations that are highlighted, and then in that first decision and find item, sub less than size. We had that before. So the main addition to our logic in find item is once we find the item, in addition to setting found it to yes or true, we need to set the price to whatever the location is associated with that part in valid prices. So they've highlighted the one change that we had to make to the find item module. In pseudocode, they've just highlighted the changes that would need to be made to use parallel arrays. So searching can be a very slow process, especially if you have many items in your arrays. We're working with relatively small arrays in these examples, but you might have thousands, tens of thousands, millions, or billions of elements in an array that you need to process. And that takes time, especially if you have to look at every element of the array. So to improve your search efficiency, the first thing you should do is what I pointed out in the very first flowchart. Once you have the answer, exit out of the loop and continue on. Again, very similar to the thought behind short circuit operators in logical expressions. If you know that a variable is going to be a specific value, then set it to that particular value instead of calculating it. These things improve efficiency of your program. And again, if you improve efficiency on a 6-element array, that's nice. It's a little better. But if you then scale that to 10,000, the savings are going to increase, by a factor of thousands in that case. So here on slide 30, in the highlighted green box, is exactly what I told you I would do before. If the sub size or the subscript is less than size, and I have not found the item yet, then look at the next element in the array. There's still one problem related to using parallel arrays, and I don't know if they're going to talk about it, so I'll go ahead and mention it. So let's say we found our item in subscript 4. So we pull the price from subscript 4, and we go ahead and increment sub to 5. We go to the highlighted decision box, we fall out of the loop, and we're indicating that we found it, but the subscript is set to 5. So it would be very easy to use that subscript to pull a price out, and you would actually get the price for the next item instead of the correct price. So often what you would do is right after that decision block, you would say sub equals sub minus 1 if you're using parallel arrays to get your subscript that's being stored in the sub variable back to the correct value to use for accessing one of your associated parallel arrays. Here they've just shown you the same thing, how you would represent this or write this in pseudocode. Working through ranges, there may be a different thing. The ranges of values in an array might be a slight bit misleading. In first read, I would read that as I'm working with a subset of the items stored in the array instead of the entire array. That's not really what they mean. Let's look at the first example. So kind of using the first example and the first bulleted point. If somebody is ordering 1 through 5 elements, they would get 0 discount. If they ordered 20 through 30, maybe they get a 25% discount. So basically what they're doing is they want to have ranges associated so that you can give a discount based on the quantity ordered, for example. Now then, what you could do is you could have an array and say index 1, 2, 3, 4, and 5 in the parallel array are all going to have the value 0 because there's no discount. And then 6 through 19, you would go, let's say 15, 15, 15, 15, 15, etc. to say there's a 15%. And then in 20, 21 through 30, you would put whatever I said before. I think 25, 25, 25, 25 to represent a 25% discount. So that's basically what they're showing right here. They've given you a quantity ordered versus discount received, and they've created a 76 element array and put all these values in it. Now what we would really like to do is have 2 arrays. In the discount arrays we would put what the discounts were, and then what we would do is we would put the maximum number of items ordered for you to receive that discount. So in this case, up to 9 you get a 10% discount. Up to less than 13 you get a 15. Up to 26 or below, or 26 or more, you get a 20% discount. So I guess I misread that. The limit is the starting point for the discount. So 9 or more is 10, 13 or more is 15, 26 is 20. Sorry about that. So in the first case, the array is very large. It uses a lot of memory. We have the same value that is stored repeatedly. And, do we have enough to give the person discounts? I suspect if the person ordered 100 items, they're probably going to get a bigger discount than was in the program. And there's different ways to handle that. Go ahead and expand the table expand their arrays to do that, or kind of kick it out and say, hey, you're ordering a whole lot. You can probably get a special discount. Maybe you want to place the order over the phone or get a quote from us in email, so that a person can handle that and decide what the appropriate discount might be. It uses a lot of memory because we have lots of elements in the array. And the other thing is, what if you change this? What if you go into that table and say, we want to give less of a discount and change the limits to smaller values? You would have to go back and change that great big array. Worse yet, if you said, okay, instead of a 15% discount, we're going to make it 18%, then you have to go in and change all those 15s to 18s. Whereas if you have the 4-element discount array, you would just need to change one value in the array, or one value in the array initialization in your program. Then what we do is we loop through, like we did to make comparisons. Again, I'm just going to repeat this because searching is a very important thing. We would search through the array by making comparisons to find the appropriate discount. So here's the code for doing that. The quote interesting part or new part of the picture is this determine discount. So what we're going to do is we are actually going to start at the end of the array and go backwards, so that we don't have to say, okay, they get a 10% discount. Oh, no, they ordered 14 items. They get a 15% discount. Oh, no, they ordered 27. They get a 20. So what we're going to do is we're going to start at the end of the array and go backwards. So what we do is x equals size minus 1 is getting the index of the last element of the array, and we say, is the quantity less than what's shown in the limits array? If the answer is yes, they've ordered less items, in this case less than 26. So we decrement x down to 3, and then we go back and say, okay, in the third element of the array, did they order more than what's in the third element of the limits, which is 13? And if so, then the answer to this comparison would be no. We would fall out and we would tell them what their discount rate was, and then prompt for a new quantity and go back and repeat the process. Not sure why they did not highlight it, but here's the exact same arrays. The array searching in pseudocode. And again, most of the interesting stuff is going to happen down in determine discount. So that's just showing you the same thing they showed you previously with a flow chart. Now then, we refer to the bounds of the array as being inside the array. So arrays in most languages have a finite size. It's not always true, but we'll assume it is for this, and it's definitely true for BASIC. That size tells how many elements are in the array. And I don't really like the way they've worded this second subpoint. You can perform a calculation based upon the array size and the data type to find out how many bytes are in an array. You can't just say, they kind of imply, oh, it's a 20 element array, that takes up 20 bytes of memory. That is probably not the case in most instances. Again, we have to have same type data. We can't have a few locations that are strings and a few locations that are numbers and a few locations that are Boolean true-false values. Either they're all Booleans, they're all strings, they're all numbers, etc., depending upon what data types the language you're working in has. Each of those elements, since they are the same type, will occupy the same amount of memory. Once you know that size of memory, how many bytes it is, then if you multiply it by the size of the array, like I said before, you will get the total amount of memory that that array is using. And the computer does math. Basically, this is probably a little beyond the scope of the class, but they kind of allude to it here in the last point. If I want access to location 4 of my array, and each location contains 10 bytes, I will find the location where my array starts. I will then subtract 1 off the location. No, actually, the location is fine. I will multiply it by the size of each, which is 50, and then I will add that to the start location of the array in memory, and that answer will give me the start of location, or index 5. So basically you do math to figure out what portion of memory. Once you got to that memory location, you would know that you needed to, in this example, read 10 bytes. And then you have the 5th element of the array. The first point, when you write your program, it's kind of going to assume that every number entered by the user is valid. That is a very bad mistake to make. Any user input should be validated. If they're giving you a employee number, and your employee numbers are sequential in an array, if they give you a value that's less than 0, or they give you a value that is equal to the size of the array or greater, you are out of bounds. That means you're not trying to access something that's actually stored in the array. What happens if you do that? A lot of languages will stop execution and give you an error. I'm pretty confident that's what Chipmunk Basic is going to do, or any basic compiler. Other languages will just perform the math calculation, assume you know what you're doing, and then access a memory location outside of an array. So if you're reading data, you'll get some random garbage value. If you're writing something, you may actually destroy another part of your program by overriding it, or other data stored, other variables, by overriding it. Syntactically, we can write a program that will access an outside the array memory location. This is a logic error, and basically that logic error is called an out-of-bounds error, as we've been discussing. Your program, as I mentioned, should check for that and make sure that this never ever happens. So in this case, a very common thing to do when you're new with arrays is to make the assumption that, my array has 3 elements, so the last index of the array is 3. Most modern programming languages, indexes start at 0. So if the size was 3, we should never access a location that is higher than 2. Here is another example. Again, it would be very easy to make the mistake to say, months, there's 12 months, I declare my array 12, and to get December I need to access location 12. So here you really need to subtract 1 off that number to make sure you're in the array. And of course earlier I told you a way that you don't have to perform that calculation, and 12 would actually be December. Now then, we've talked about going through a loop, and we did that before. So what happens is, we've had while loops, and at this point, if you don't know about the for loop, you would probably use a while loop. While the index variable that's going through various indexes of your array is less than the size of the array, I want to continue looping. Well, since iteration, which is going over or processing an array, is a very common thing, we're going to learn about a new statement or a new loop called the for loop. And they use this and teach you about this at this point because it is very, very often used in working with arrays. You need to make sure you stay within the array bounds, again, remembering that arrays start at 0. And the highest usable subscript is 1 less than the array size. I think an example, back to the first bullet point, is going to show us better. But what happens is we have something called a loop control variable that we talked about before that is going to determine whether we stay in the loop or not. It initializes that to some value. It then does a comparison to compare it to some limit, in this case the size of the array. And then at the end of the loop, it alters it by adding 1 to it or subtracting 1 to it, or whatever we need to do to match up with the logic of our array. So here is our departments. We have 5 departments. And if we need to process or print out each department name, we can say for department equals 0. So there's 2 things that happen in the department equals 0, or DEP equals 0. First, we have our loop variable, DEP, and we initialize it to 0. And we want to go from 0 through size minus 1. And each time we hit the end for loop, we want to do step 1, which means increment it by 1. Actually, in most languages, you could omit the step if the step is 1, because that's the most common thing to do, is increment by 1. So in this case, the department loop control variable would go 0, 1, 2, 3, 4. And each time for each of those values, it would output the corresponding department name. So you can see how short that is and how easy that is to follow just by reading it. You could probably show this to somebody who's not a programmer type, and they could probably make a very reasonable guess as to what this pseudocode was trying to accomplish. Okay. So they're just going back and talking about the various pieces which you've already done and saying that a for loop is much more efficient. So that finishes up Chapter 6. We now know a lot about arrays. We know how to use constants in relationship to arrays. And we've had our first exposure to something called searching, which is going through and processing elements of an array or looking for elements. We learned about setting flags to be a little more efficient and not process elements of the array that we don't need to process or should not. We learned about parallel arrays, and then we also learned how to do range comparisons using parallel arrays. So, like I said, that finishes up Chapter 6.